We are now going to look at the boundary between two materials and what happens to the magnetic fields on the two sides of the boundary. We can represent our magnetic fields in the two materials as the sum of a tangential component and a normal component. So we can do that with the magnetic flux density field or the magnetic field intensities. We will define the angle that the magnetic fields make at the boundary as the angle between the field and a surface normal. To determine the condition on the normal component, we're going to apply the Maxwell equation. The integral of B dot ds is equal to 0. Our Gaussian surface will have this form. The tangential components go in and come out, so the integral of B dot ds around the sides of our cylinder will be 0. On the top surface, B sub 1 normal is in the same direction as the outward normal, so the integral of B dot ds around the top surface is going to be B sub 1 normal times delta S. On the bottom surface, B sub 2 normal is in the opposite direction of delta S, so the integral of B dot ds around the bottom surface is going to be minus B sub 2 normal delta S. So B sub 1 normal is equal to B sub 2 normal, so we see the normal components of the magnetic flux density field will be continuous. For the magnetic flux density fields, let's substitute the absolute permittivity times the magnetic field intensity. So we see that the normal components of the magnetic field intensities will be discontinuous at the boundary. To get the relationship for the tangential components of the magnetic fields, we're going to apply Ampere's circuital law. We will choose an Amperian loop that runs parallel or normal to our interface. We are also going to include the possibility that there could be a surface current density flowing along the boundary. When we integrate from A to B, we'll get H sub 1 tangential times delta W. When we integrate from B to the interface, we'll get minus H sub 1 normal times delta H over 2. And the minus sign is because our defined H sub 1 is in the opposite direction of our integration. From the interface to C, we'll get minus H sub 2 normal times delta H over 2. When we go from C to D, we'll get minus H sub 2 tangential times delta W. From D to the interface, H sub 2 normal times delta H over 2. And from the interface to A, H sub 1 normal times delta H over 2. We defined our surface current density as flowing into the page, so if you put the fingers of your right hand in the direction of our integration, this clockwise direction, your right thumb points into the page. So the current inside our Amperian loop that is flowing into the page is K times delta W. So these terms sum to 0. And we can go now and divide both sides of our equation by delta W. So we're left with H sub 1 tangential minus H sub 2 tangential is equal to our surface current density. If our surface current density is 0, we see then our tangential components of the magnetic field intensity are continuous. So let's replace the magnetic field intensities with the magnetic flux density field divided by the absolute permeabilities. And we see the magnetic flux density field's tangential components will be discontinuous at the boundary. So here are our results for the normal components and tangential components of our magnetic fields. So looking at this figure, we can rewrite H sub 1 normal as H1 times the cosine of theta sub 1. And for H2 normal here, we can rewrite that as H2 times the cosine of theta 2. In this equation, we can rewrite H sub 1 tangential as H sub 1 times the sine of theta sub 1. We can rewrite H sub 2 tangential as H sub 2 times the sine of theta sub 2. Let's now take this equation and divide it by this equation. On the left-hand side of the equation, we will cancel the H sub 1's, and on the right-hand side of the equation, we will cancel the H sub 2's. Let's rewrite the sine over the cosine on both sides of the equation as the tangent of theta sub 1 on the left side and tangent of theta sub 2 on the right side. We get a relationship between the angles of the magnetic fields on the two sides of the boundaries and the absolute permeabilities of the two materials. This equation gives us the refraction condition for the magnetic fields across the boundary.